All right. So today we're going to go over section 8.3, which is going to teach you how to graph a polynomial function. The first thing you'll need to graph a polynomial function is something we've done before already called the end behavior. So let me review that with you really quick. So when a polynomial has a degree that is odd, like an exponent, like the highest degree is something odd, the end behavior is like a line, which is called down up. So for example, here's a line that has a positive slope. So that polynomial has a positive coefficient with an odd degree. So all of these have positive coefficients with odd degrees because they're all what's called down up. Down up. Okay, next, when the polynomial has a negative coefficient, but still it has a odd degree, so an odd exponent, they are called up-down. So for example, like a negative x. So this is a negative x, and it has a end behavior called up-down. You will have to type those on your progressive test. I think just like the U and the D. So this one's up-down. This one's up-down. So again, that's called the end behavior. So positive coefficients with odd exponents have a down-up behavior. Negative coefficients with an odd exponent have up-down behavior. And then same thing for the even degrees. When a degree of the polynomial is even, so when the exponent is even, the end behavior behaves like a parabola, so like this, called up-up. If your coefficient is positive, or down-down if your coefficient is negative. So all of these have an up-up behavior, and all of these have a down-down behavior. So that was just a review of what's called end behavior. Today, we're going to do that plus something called a root behavior. Okay. So here goes what's called a root behavior. I'll read you the directions, and then I'll show you a visual of it. So root behavior. It says the real root, or the zeros, which is where the graph crosses the x-axis. So the roots are called the x-intercepts. So the real roots, or the zeros, of a polynomial are the x-intercepts. If a real root occurs as a root an odd number of times, the graph will cross the x-axis at that point. The multiplicity of the root will determine how the graph appears as it crosses. Okay, so let me try to show you a visual of what that looks like. So pretend that your polynomial has like a, let's say like an x minus 1. So the root here would be 1, 0. And then since it's just, this is what's called an odd number of times, like it just happens once. So your graph will just cross the x-axis at that point, at 1. So that's what it says, crosses the x-axis at that point. The multiplicity of the root determines how the graph appears as it passes through the x-axis. So let me give you that example. So on this one, let's do x minus 1 to the third. Okay, so this degree is still an odd number of times because, first of all, x minus 1 to the first, that's an odd number of times. X minus 1 to the third, that's still an odd number of times because 3 is odd. But when you graph x minus 1 to the third, the x-intercept is still 1. Like you still go here to 1. However, it's not going to cross straight through like a line did. It's going to cross with that inflection point thing. So it's going to go like this and like that. So it's still crossing the x-axis, but it crosses...
For me.
What?
Your screen's frozen for me.
Who's me? Who? Who's talking?
Yeah, for me too, Miss Garcia.
So for the whole class. Okay, let me try to fix it. Okay, so we're just gonna start. Okay, let me just review really quick. So like I told you, when the root has an odd power, like 1, 3, 5, 7, your graph will cross the x-axis. If the power is just to the first power, the graph will cross straight through like a line. But if the power is anything else odd that's more than 1, like 3, 5, 7, 9, 11, your graph is going to cross like a cubic. So make sure you know that. Next, when your exponent is even, like 2, 4, 6, instead of your graph crossing the x-axis, it's going to do what's called bounces. Make sure you know that because you will have this term on your progressive test. So bouncing off the axis means that you're graphing and then at your root, so here the root is 1, instead of crossing the x-axis, it bounces right off. So let me show you another one. So this one, let's do, actually let's do like a negative x minus 3 to the 4th. Or actually let's change it to x plus 3 just because. All right, so let me show you what this one looks like. So negative x plus 3 to the 4th, for starters, the root is negative 3. So you put a dot at negative 3. Next, because it is negative, the graph is going to open down, like down behavior. And it's going to look like this. Okay, that's what's called bouncing off the axis. It touches the x-axis, but it doesn't cross it. It just bounces back off. So that's what's called even multiplicities bounce off the axis. So there's 2 examples. And that's how you're going to graph polynomials. And then the last thing I need to tell you before we actually do an example is imaginary roots cannot be graphed on the real plane, so we're not going to graph them. So let's just actually just do an example. So example 1 on the back. Hopefully the camera is being good and you can see this. Example 1. Let's go ahead and graph this situation here. So number 1 has a polynomial with several roots. I have a 3x squared, so that means that 0 is a root. Since x is a factor here, that means that 0 is a root. And notice how its power is even, so I like to write like a little tiny baby 2 here as a subscript. You don't have to write it, but it's going to help you because now we know that at 0, the graph should bounce off the axis because this power of 2 is even. So let's continue. The next root is going to come from x plus 5, so that means that negative 5 is a root. That power is just a 1, so you can write a little baby 1 right there. So that means that at negative 5, the graph will cross the x-axis like a line because the power is 1. Finally, 2x minus 5 to the 4th. That means that the root is positive 5/2 with a little tiny degree of 4. So this one means that on the graph, on the x-axis at the 5/2, since it is even, it will not cross the x-axis. It's just going to bounce off the x-axis. Next, find the y-intercept. The y-intercept is just when x is 0. So if you plug in 0 times 0 plus 5 times, it looks like it's just going to be 0. Because if you plug in 0 for x here, you're multiplying 0 times whatever is 0. Next, the leading term. Okay, so for the leading term, we're going to have to try to like FOIL this out, but not all the way. So the leading term should be in standard form. Like for example, that's my leading term right there. So right now, I need to pretend like I'm going to FOIL this out. So here's how you would do it. You would take the 3x squared times this x times this 2x to the 4th. That is going to give you the leading term. And we will need the leading term to graph. So if I multiply 3x squared times x times 2x to the 4th, 2x to the fourth, 16. 16 times 3, 48. So positive 48. X squared times x to the fourth, 4, 5, 6, 7. X to the seventh. So my leading term is a positive 48 x to the seventh. So that you need to remember the end behavior for those is down up, because it is a positive coefficient with an odd exponent. So it looks like a down up behavior. Oh, and I guess that's what I needed here. The sign of the leading coefficient is positive, and the degree of the polynomial is, you can just call it odd, or you can put 7 if you want. Either one is correct. So now that's all you need to graph. Let's try it. So the way you would graph this, for starters, I go ahead and graph all the roots. 0, -5. You can just eyeball it. 5/2. Next, graph the y-intercept. 0, 0. It's already graphed. Finally, what I like to do is I like to graph this end behavior. So I know it's going to be down up. So that means that like my graph is going to start like down here and end up here. So that's called down up. Now I'm ready to start connecting all my stuff. So when I start connecting it, I'm going to start down here on the negative infinity area, so the down. I'm going to go to -5. So remember, at -5, the exponent was just a 1. So that means that your graph should cross the x-axis like a line does, so straight through, like that. And these are just sketches, so it doesn't matter how, like, exactly how it looks, as long as that at -5 it crosses the x-axis. So next, your graph is going to have to be pulled down towards this towards the next root. So it's going to come back down to this, to here, to 0, 0. So at 0, the exponent is even. So when the exponents are even, that means that the root will bounce off the axis. So that means, first of all, let me put 0 here. So that means that here on the x-axis, your graph will bounce right back up. And then, like I said, it doesn't matter like how you sketch this part. Okay, next, the graph will be pulled towards the other root of 5/2. So you need to come down here. 5/2. At 5/2, the exponent was even again, so 4. And again, even roots or even multiplicities of the roots tell you to bounce off the axis. So here at 5/2, and you're going to bounce right back up, which makes sense because you're just going to connect it to that up behavior. So it will look like that. And that's just a sketch. Yours is not going to be exactly the same, but it just, at the 5/2, the graph needs to bounce. And on the test, that's all I'm going to ask you. Like, I'm going to ask you, like, at the 5/2, does the graph cross or bounces? You're going to put bounces. At 0, does the graph cross or bounces? You're going to put bounces. At -5, does the graph cross or bounces? You're going to say crosses. And that's really all you're expected to do on the test, plus the end behavior. So I will ask you, what is the end behavior? And you'll tell me down, up. So let me pause for questions. Okay, next try. Example 2. We need to graph this polynomial by first finding the roots. So like I explained on example 1, take each of the factors and set them equal to 0 so that you can find the roots. So you start with this one, the square root of 2 minus x, set it equal to 0, and solve for x. That's just going to be the square root of 2. I skipped the first one, the 2, because 2, that doesn't equal 0, so that's not part of the roots. Next root, x. Oh, and then don't forget to put like the little baby 1, because the square root of 2 minus x is raised to the first power, so that's the multiplicity, 1. X plus the square root of 2, set that equal to 0. That's going to give you a negative square root of 2. Again with the little baby 1, because that factor is being raised to the first power, so that's its multiplicity. Finally, x plus 1, set that equal to 0, that would be -1. That factor is being raised to the second power, so that's its multiplicity. And those multiplicities matter because when the multiplicities are odd, like 1, your graph will cross the x-axis at those roots. But when the multiplicities are even, like this one, the graph will like bounce off the x-axis. So let's just keep going. The y-intercept. So for the y-intercept, you're supposed to plug in 0 for x. So maybe I need to do that one. So y equals 2 times the square root of 2 minus 0 times 0 plus the square root of 2, so just square root of 2. And then 0 plus 1 squared. So if you plug in 0 here for x and simplify, you'll get y equals 2 times the square root of 2 times the square root of 2 times 1 squared. So that's just 4. That's the y-intercept. Next, the leading term, you'll do what I showed you in example 1. You need to try to take the, you need to try to FOIL this whole thing out, and here's how you would do that one. You do need to take into account this first 2, so it's going to be 2. And then in the square root of 2 minus x, the leading term there is the minus x. So you have to multiply by a minus x. Next, on the next parentheses, x plus the square root of 2, the leading coefficient there is x. So you multiply by x. And then finally, on the last one, the leading coefficient is x squared. So you multiply by x squared. This is going to give you the leading term. So you multiply that out. It's going to be a -2 x to the 4th. So the sign of the leading coefficient is negative, and the degree is even. So since you have negative even, that's called down, down. So one more time, here's how I graph. The first thing I do is I graph the roots. And you can just eyeball the square root of 2. The square root of 2 is a little bit more than 1. So just put it there. Negative square root of 2. That's going to be like negative 1 point something. So negative square root of 2. Negative 1 will just be right there. It's just a sketch, so they don't have to be perfect. So after you graph the roots, now graph the y-intercept, 0, 4. Right here. After you graph the y-intercept, go ahead and graph the end behavior. So the end behavior of this thing is called down, down. So it's going to end down here, or start down and end down. And now you start connecting everything. I always start with the down here. So connect that to your first root. At -2, or not -2, negative square root of 2. At negative square root of 2, the multiplicity is 1. So that means that your graph will cross the x-axis like a line. So it's just supposed to cross straight through like a line. There we go. There you go. And then your graph is going to come towards this -1 root. Like you can't just go on forever. Like it needs to come back down to the root. So right here. At -1, the multiplicity is even because there's a 2 here. So that means that your graph bounces off the axis. So it's going to bounce back up, probably towards that one. Fine, whatever. It's just called bounces. Next, it's going to connect to the y-intercept. And after that, the graph will, it can go up a little bit, but it has to come back down to this root. Right there, the square root of 2. So at the square root of 2, the multiplicity is 1, so your graph should cross like a line. Like that. And again, since you're doing like the online test, I'm not going to really make you, I'm not going to grade your graph. I'm just going to grade, it's going to ask you like, at the square root of 2, does the graph cross or bounces? You're going to say crosses. At -1, does the graph cross or bounces? You're going to say bounces. And then finally, at negative square root of 2, does the graph cross or bounces? It crosses. and it will ask for the end behavior. So that would be the end behavior. I'm going to pause for questions, and then we're going to try another example. Okay, so let's try another example. So we're still doing the same thing. We're going to be graphing. Example 3. So the bad news is that example 3 is not in factored form, so we can't tell the roots right away. Example 1 and 2 were already in factors, so we could tell the roots right away by setting each factor equal to 0 and solving for x. Okay, now example 3 and example 4, they're not in factored form, so we're going to have to find the roots first. And the way you find the roots is what I've been teaching you, I guess, last week. And so let's just do it. So here it goes, example 3. I need you to make a list of the possible rational roots. So that's going to require like a little plus or minus thingy. And then the way you make the list of the possible rational roots is you take the factors of the constant. So the constant is 1, the constant is 2. So the factors are 1 and 2. And then you divide them by the factors of the leading coefficient. The leading coefficient is just a 1. So basically you just take 1 and 2 and divide them by 1. So it's just 1 and 2. So that's great. Next, you do a P and I chart. There's a video that you're supposed to watch over P and I charts. Do it because you need to do one of these on the progressive test. P stands for positive roots. N stands for negative roots. I stands for imaginary roots. So here's how you make a P and I chart. You start with the P, positive roots. According to some theorem, the number of positive roots is equal to the number of sign changes that your polynomial has. So if you look at all these terms, you want to see and count how many times they switch signs, like from positive to negative or negative to positive. Okay, obviously all of these signs are positive. So there was 0 sign changes. So that means that this polynomial has 0 positive roots. So positive 1 and positive 2 will not be roots, so we're not going to divide by those. So 0. Next, the negative roots. So according to the theorem, or I think it's called I don't even know what this name is called, but anyway, for the theorem, the number of negative roots is equal to the number of sign changes of P of negative x. So what we're going to have to do first here is, and I'll just do it down here, I guess. I need to take in a negative x and plug it into my polynomial. And again, there's a video just on this. Watch it. So if I take negative x and plug it in here, this is going to be negative x to the 4th plus 3 times negative x to the 3rd plus 3 times negative x squared plus 3 times negative x plus a 2. So now I want to count how many times those terms switch signs. Before you do that, I like to simplify it. So negative x to the 4th, that's going to be a positive term. Plus 3 times negative x to the 3rd, that's going to be a negative term because negative x cubed is negative. Plus 3 times negative x squared, that's going to be another positive term because anytime you have a negative being squared or raised to an even power, it becomes positive. Next, you have 3 times negative x. That's a negative term. And finally, you have a positive 2. Okay, so now you count how many times your term switched signs. So for the last time, there's a video just on this. Watch it. So from positive to negative, that's 1 sign changed. From negative to positive, that's a 2nd sign change. From positive to negative, that's a 3rd sign change. And from negative to positive, that's a 4th sign change. So this thing changed signs 4 times for your negative x. So that means that the number of negative roots is 4 or less than that by an even number. That's the theorem. The number of roots is equal to the number of sign changes or less than that by an even number. So that means 4 or 2 or 0. So this column here has 4 or 2 or 0. And now to finish filling the rest of the chart, yes, you have to do one of these on your progressive test. So remember, the polynomial is a quartic. It has 4 roots. So if the polynomial has 0 positive roots and 4 negative roots, that's already all 4 roots, and therefore there won't be any imaginary. So that's just my first row, 0, 4, 0. Next, for the next row, the number of positive roots is always 0, so it's just going to be 0 here all the time. So if the polynomial has 0 positive roots and 2 negative roots, that means that I'm still missing 2 roots because there should be 4. So that means that it could have 2 imaginary and 2 negatives. So that's another possibility. And finally, the last row, if the polynomial had 0 positive roots, 0 negative roots, then that means that all 4 roots are imaginary. This is called a P&I chart. It describes the possible solutions. So your polynomial could have 0 positives, 4 negatives, and 0 imaginaries. Or it could have 0 positives, 2 negatives, and 2 imaginaries. So we're about to figure out which one is the right one by actually finding the roots. So the way you actually find the roots is what I taught you probably last week. You need to synthetically divide your polynomial by the possible rational roots until you find some roots. So remember, the polynomial has 0 positive roots, so do not divide by positive 1. Instead, divide by negative 1. So do it. Take the polynomial 1, 3, 3, 3, 2, and synthetically divide by negative 1. And that's going to have to be a root. So let's do it. Negative 1, 2, negative 2, 1, negative 1, 2, negative 2, 0. So yes, negative 1 is a root. And then like I showed you again last week, once you found a root, then make sure you use the reduced cubic. So this right here is a cubic because it's no longer a quartic. You've narrowed it down to a cubic. So use this reduced cubic here. Let me write it down. 1x cubed plus 2x squared plus x plus 2. So use this cubic to keep finding the roots. So remember, don't divide by positive 1 nor positive 2 because those don't work. There's 0 positive roots. So I would divide by negative 1 again to make sure that it's not a double root because that's possible. And I think that's example 4. You'll have a double root there. So let's just try it. Negative 1 again. I want to see if negative 1 is a double root. Negative 1, 1, negative 1, 0, 0. No. So negative 1 is not a double root. So negative 1, not a double root. So that means like right here, its multiplicity is just a 1. Okay, now negative 1 didn't work, so try negative 2 on the cubic. So I am going to divide the cubic, so the reduced cubic, by negative 2 this time. 1, negative 2, 0, 0, 1, negative 2, 0. That one did work. So negative 2 is a root. Finally, we're not going to check if negative 2 is a double root because what we're going to do is just write my quadratic and find the remaining 2 roots, and then you'll know whether negative 2 is a double root or not, if negative 2 is an answer again. So let's go ahead and write down my quadratic to find the remaining 2 roots. So this quadratic is, the quadratic would be 1x squared plus 0x plus 1. Okay, so that's my quadratic. So in order to find the roots of a quadratic, you either factor, which that's not going to factor because that's a sum. You use the quadratic formula, you complete the square, or this one we can just set it equal to 0 and solve. So set that equal to 0 and like square root property this, subtract 1. Take the square root on both sides. So that's going to be absolute value of x equals, the square root of negative 1 is called I. So the remaining two roots are plus or minus I. So positive I and negative I. Those are called imaginary roots. Imaginary roots, you're going to list them here, but imaginary roots cannot be graphed on a real grid. But you still list them as part of your roots. So finally, I have found all four roots. And since there are four different roots, that means each of those multiplicities are just to the first power, because they have to add up to 4 total roots. So after all that work, I just need to find the y-intercept and then I'm ready to graph. The y-intercept should be easy because it's just going to be this constant 2. So if I plug in 0 for x on all of these, you just get 2. So let's practice graphing. The way you graph, you first graph the actual roots on the number line. So negative 1, negative 2, and then you cannot graph imaginary roots. Next, you want to find that leading coefficient. So I forgot to write it as part of your work, but x to the 4th, that's a positive x to the 4th. That's called up, up. So I like to draw the up and up. And last thing was the y-intercept. 0,2. And now you just sketch the picture. And again, on the test, you just need to tell me what is the end behavior. So you would have to say up, up. And then you would have to tell me whether the graph crosses or bounces. So let's start with negative 2. That's just to the first power. So it crosses straight like a line. And then the graph has to come back up to negative 1. Crosses straight like a line. Okay. That doesn't matter how you curve it. It doesn't matter. So on my answer key, I think it looks prettier. It looks like this. They're both correct. They're just sketches. I need to rescan my answer key because the one that's in Schoology right now is not updated. So after I teach you today, I'm going to rescan the updated answer key. So number 3, the sketch looks like this. And then I'm just going to very quickly graph the last one. I'm not going to spend time finding all the info. I'm just going to give you the info, and then we're just going to graph it. So last example, example 4. We're supposed to do everything I did on example 3, but we don't have enough time. So I'm just going to tell you what the answers should be. So example 4, make the list of possible rational roots. Plus or minus. Pretend we already did them. They are 1, 2, 1/2. Make sure you list them in order on the progressive test, like ascending. So put the 1/2 first, 1, 2, just so that the computer grades it right. Letter B, make a P&I chart. Okay, I don't have time to do it, so you're just gonna have to copy my answer key. Positive, there was 0 roots. Negative, there was 4 changes again. So 4 or less than that by an even number. Each row of the P&I needs to add up to 4 because this is a quartic. So that's 0, 2, 4. Next, we need to find the roots. You need to find the roots by doing the synthetic division thing. Just pretend I already did it, and here are the answers. Negative 2 with the multiplicity of 1. Negative 1/2 with the multiplicity of 1. And then this is the one that I was talking about. Negative 1 is a double root. And you would notice that it was a double root because when you synthetically divide by negative 1, you'll get a remainder of 0. And then when you take that reduced answer and synthetically divide by negative 1 again, you'll get a remainder of 0 again. So that's called a double root. So do it on your own. Finally, y-intercept is still 2. So example 4 is almost like example 3. Pretty much almost the same. Yeah, pretty much the same because the leading coefficient is positive even, so that's called up, up. Up, up. And now here's how you graph it. Graph the roots. So -2, -1, and then -f. Let me move my in behavior this way. So now you start sketching it. At -2, the multiplicity is a 1, so that means odd. It crosses straight through like a line. At -1, the multiplicity is even, so that means it bounces off without crossing, so it's going to go back down like that. And finally, at -1/2, the multiplicity is odd, so it's going to come and cross straight like a line. Oh, and then don't forget the y-intercept of 0, 2. So, like that. And that's how you graph polynomials. So this is called 8.3. You would just practice this before the progressive test, since that's not on today's quiz. So practice 8.3.